Hey, welcome back everyone. It is Christmas, so Merry Christmas. Hope you guys are having a great time with your family and friends. Back on the Sleeper project. Tonight is Pistons, and specifically the four pistons that I'm going to be using in the project, the set that I've damaged, and a sort of very mathematical look in what I'm calling 1 second in the life of a piston, which is very maths heavy, and I know it's the holidays, so grab a beer, grab a glass of wine, and let's get into it. It is quite math heavy because it is 1 second in the life of a piston at maximum torque, maximum horsepower, and maximum RPM. But it is really, really interesting, so let's check it out. So, the Punto GT motor we will be using generates 208 Newton meters at 3000 RPM and 134 brake horsepower or 100 kilowatts at 5750 RPM. Now what that actually means is this is factory quoted power, which is at the flywheel. Before, it's lost power in the gearbox, lost power in the diff, lost power in the drive shafts, lost power on the wheels, and eventually getting power to the road. So we'll have to get it on a dyno to see what the actual on-the-road figures are once this is built. And what that essentially means, this Newton meters, is if you have a pivot point, let's say over there, and then 1 meter away, you put 208 newtons of force down on that point. Think of it like a big spanner. So you put 208 newtons on that point and it pivots about there. The force that's felt at that point. That is the meaning of the Newton meters. So let's do what it takes for this motor to maintain 208 Newton meters for 1 second. So 3000 RPM is revolutions per minute. So that's the same as 50 revolutions per second, as we are wanting to calculate for 1 second. And because one revolution has 2 power strokes in it, that means 1 second equals 100 power strokes. So that means 1 second at 208 Newton meters equals 100 power strokes. Let that sink in. And now to discuss that 134 bhp. So we know this is at 5750 RPM, which is the same as 95.83 revolutions per second. And as we know, 1 revolution equals 2 power strokes, we can say that 1 second at 134 bhp equals 191.667 power strokes. Okay, so looking at the max RPM, I pre-drew this little image and I am planning on running a maximum of 7000 RPM, which is 116.667 revolutions per second. So it'll turn 116.6 times every second. Now, because we know that 1 stroke is 64.7 millimeters and 1 revolution is a downstroke and an upstroke, we know that 1 rev, my bad, equals 134.8 millimeters. So if we have 1 revolution is 134 and we have 116 revolutions every second, that means that 1 second equates to 15,726 millimeters traveled by the piston. So that is 15.726 meters, and we know that it's every second, so it's 15.7 meters per second, which is also 56.6 kilometers per hour. So that means that the piston will go from its top position to its bottom position, starting at 0, ending at 0, averaging 56.6 in that time, and it will do that 233 times every second. So if you think about the G-force involved with regards to going from an absolute standstill, averaging 56.6 kilometers an hour. Now, of course, that does not mean that's the peak, that's the average. And slowing back down to 0, 233 times every second. You think about the G-forces involved on the conrod that attaches to the piston itself with regards to the friction on the cylinder sidewalls. You think about the pressure from the exploding gases, the upward pressure from the conrod not wanting to turn because of the weight of the vehicle. So all of the forces that are actually acting on the piston, it is genuinely mind-blowing that this thing doesn't just turn to, I don't know, Play-Doh and just fall apart. It is seriously impressive. So while the pistons are doing this up and down dance, that's actually where the power is made, and it's made through a series of 4 strokes, and these are them roughly: the inlet stroke, the compression stroke, the power stroke, and the exhaust stroke. And when the exhaust stroke ends, back to the power stroke. So I'll take you through them in a very short way. There's 1,000 videos on the internet. If you want more detail, go check it out. This is the short story. The 4 strokes of the engine: inlet, compression, power, exhaust. This is actually just a really well timed, well choreographed dance. So the inlet stroke begins with the piston roughly top dead center. The cam will align to press down the valve, breaking the seal, allowing air to pick up fuel as the piston draws down, filling this chamber with air-fuel mixture. Once the piston gets down to bottom dead center, thereabout, the cam will turn away, the valve will close. Now this is a sealed chamber, and the compression or the squeeze stroke will start, and the piston will move back up, squeezing the contents of this into a very small pocket. And then the power stroke. As the piston is coming close to top dead center, the spark plug will fire, detonating or exploding, expanding the gases that are there, driving the piston down through the power stroke. Once the piston gets to the bottom of the power stroke, close to bottom dead center, the piston will start to come back up. Now the exhaust valve will align, opening the valve, breaking the seal, and allowing the exhaust gases to flow out, and the piston will come up and drive them all out. And as it gets to the top, that is then the start of the inlet stroke. So then it's inlet, compression, power, exhaust. Suck, squeeze, bang, blow. I really want to show just how close to the head the piston actually comes while it's traveling at those speeds that it's traveling. So in this clip, you can see the piston coming close to the top. In fact, it actually looks like it's leaving the block, just by a little. So, having seen that, take into consideration that this mounts directly to that block, separated only by a gasket like this, which under compression is about 1 millimeter thick. So you've got the pistons coming as close to this head as you've just seen in that previous clip. How many times in a second to a distance so close, just missing it and putting it away. The other thing to note is when the piston does come up to here, it is taking all of that compressed air and compressing it only to the space that's inside here. So it's taking that 67.4 millimeters away from the head, and it's compressing everything into only that prior to detonation. From here, I guess there's quite a lot else in a motor that's not really very often spoken about, and that's all the extra little gearing that handles putting oil all over the motor. You can actually see that there's tiny holes in the bottom of the conrods, and they eject from there, and they will actually spray oil into the piston so that it's oil cooled from below to help it cope with the heat from above. And that oil is given through the actual crankshaft, and there's oil feed that goes all over the motor. It's really incredible how it works. So it's definitely something worth discussing. And in other news, and just a bit of a sideline, I gave the camshaft a clean. Look at how that glows in the artificial light. It is so nice. So just as a bit of a wrap up, and I guess now it's time to come clean about the breakage. Yep, I broke the piston. They are incredibly fragile. When you think about all the stuff that we've just discussed and how much this thing has to go through, all the pressures and heat and everything, you drop it 3 feet onto something thin, it's broken. So really, really strong, but in a very specific way. Yeah, so I just dropped it from, you know, half a meter, 3 feet, something like that, onto something pretty sharp, and yeah, it broke, it gave way. So that's just it. But I hope through this you guys have, I don't know, learned something new or refreshed something you already knew. I can tell you that I've always known everything happened really quickly, but when I actually did the maths, it changed everything. Now when I drive my car, I really look at the rev gauge and it's like, wow, I'm doing 3,000 RPM. Ooh, I feel bad, change gears. You know, so I'm crawling around at 1,500 RPM just to try and reduce wear and tear. So it's mind-opening, and I think the engineers that make these things do what they do for as long as they do, you know, it's nothing short of a miracle.